Hi scholars, today we're going to problem solve with fractions. So for example, 2/3 is a fraction, 5/6 is a fraction, right? And the key idea when we're dealing with fractions is we can't really compare fractions by just comparing a 2 with a 5, for example, and saying 5 is bigger than 2, or comparing a 3 with a 6, that we really need to have the same denominators, have a common denominator, and then we can sort of compare different sizes of fractions. So here, for example, 2/3, I can rewrite that as 4/6, right? Just by multiplying the top and the bottom of this numerator and denominator by 2. And if I'm now looking at 4/6 and 5/6, now I can work with them. Now I can add them, I can subtract them, I can compare them, right? Because this 4/6 is really 4 of these things that are sixths, right? And this 5/6 is really just the same thing as 5 of these things that are sixths. So I can compare 4 of something, right? I can compare 4 apples, right, with 5 apples. It's pretty easy to do that. But I can't compare 2 oranges with 5 apples, for example, right? 2 of these things that are thirds, it's very difficult to make sense of that if I'm comparing it to something that is in the unit of sixths. Okay, so that's a big idea. So let's see how that plays out by doing a couple of examples. Example number 1. Sam has a strip of bubble tape that is 4/5 of a yard long. Here's a picture of bubble tape. I don't know if they still sell that anymore. It was very big when I was growing up. If he cuts the gum into equal pieces, each measuring 2/25 of a yard long, then how many pieces will he have? Okay, so we can do this algebraically. We can also draw a picture. So let's start with drawing a picture. So here, I'll make it even a little bigger. Here's the strip of bubble tape that Sam has, right? Let's say that each one of these is fifths, okay? So he has, right, 4/5. So let's just color that in. This right here is 4/5 of a yard, right? So if the whole tape was 1 yard, this represents in blue 4/5 of a yard, all right? There's one of those fifths, there's another one, right? You get the picture. There's another one and there's another one. Okay. He wants to cut the gum into pieces measuring 2/25. I don't have any 25ths here. However, right, I do know that in 1/5 there are 5 25ths, right? Because I can multiply top and bottom by 5. So in other words, each of these areas, right, of 1/5, I know that inside there are 5, 1, 2, 3, 4, 5 25ths. So each one of those things is 1/25, okay? And inside this one, there's also those 5, right? Inside this one, there's those 5. Inside this one, there's those 5. Altogether, how many 25th pieces are there in this whole roll of bubble tape, right? And we can count them. 1, 2, 3, 4, 5, and you'll count that there are 20 of these in here, right? So there are 20 of these 1/25th pieces. That's how long the bubble tape is. In other words, the bubble tape is 20/25, 20 25ths of a yard, right? We're dealing with yards. So this is the whole bubble tape. And now, right, that we know that it's 20 25ths and each one is measuring 2/25ths, the question is, how many 2/25ths are there in 20 25ths? Well, we could do this by counting, right? I could say, all right, here's 2 of them. Here's another 2 of them, right? And I could keep counting. Here's another 2 of them, and count. Or I can just reason that, right, if I have 2/25ths and I have 10 of those, that is equal to 20 25ths, right? Exactly what we want. That is equal to 20 25ths. And the same way, if you had counted those 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you would have found 10 of those little pieces there. Okay, so that was a lot of work. And you're saying, oh my goodness, that is really a lot of work. Is there another way to do this problem that's sort of quicker and easier? And certainly there is, right? What we could have done is we could have actually said that this is 4/5 of a yard. This is what we're starting with. 4/5 of a yard. And I want to measure it using units of 2/25. In other words, divided by 2/25. This right here is a division of fractions, right? I could rewrite division as fractions as 4/5 times 25/2, okay? Which altogether, 4 times 25 is 100. 5 times 2 is 10, right? Or else you cancel earlier, and that all equals to 10. Oh, that all equals to the answer, right? 10, which is how many of these smaller 2/25 fit into this larger 4/5 piece, okay? So if you understood that, that's great, that's wonderful. If not, take another look at this tape, this example. This idea is very important. It's important to understand this idea, and then it's also going to be important later on to be able to model equations like this sort of quickly and algebraically, right? Okay, let's do a couple more examples. Example number 2. Which is larger, 6/10 or 7/12? So here's an example where I look and I could say, oh look, 7 is bigger than 6, so 7/12 is larger, all done. And if they were measuring the same thing, then that would be correct, right? But they're not. This 7 is talking about twelfths. So you have more of them, but they're smaller, right? Twelfths are smaller than tenths. So we have to find out which is larger. And the only way that we can really compare these is to find a common denominator. So let's do it really quickly. So 6/10, we'll just keep it as 6/10. And I have 7/12 here. And if I want to find a common denominator, I could look for the least common denominator, which is fine. But here, you know what I could do? I could actually just multiply the top and bottom here by the denominator of the other one. That's another way to do it, right? So for example, I could multiply this by 12/12. And this one, because there's a 12 in here, right? And over here, I could multiply it by 10/10 because there's a 10 here, right? And what that allows us to do when we do our calculations is we're going to get some number over 120 on the left side, because 12 times 10, right, in the denominator position. And 12 times 10 is also going to be some number over 120. And now, no matter, right, since we have the same denominator, right, we have a common denominator, we can now compare the size of the numerators, common denominators. We can compare the size of the numerators immediately, and whichever one is bigger, that's the larger number. So let's see. On the top, I have 12 times 6 over here. That's 72. On top here, I have 7 times 10. That's 70. So this number is bigger, 72 over 120, or 6/10. That is your answer. 6/10 is larger, even though 6 is smaller than 7. 6/10 is larger than 7/12. It would be better to have 6/10 of a dollar than 7/12 of a dollar, for example. Let's take a look at one more example. Example number 3. If 4/3 x minus 5/6 x equals 2/5 minus 1/2, what is the value of x? Okay, this looks like a mess, but again, the theme, like we've been talking about, is that we can only do things with fractions, right? We can manipulate them if they have the same denominator, because then we're talking about the same thing. Otherwise, we're talking about apples and oranges. So I have 4/3 and I have 5/6. It would be nice if I could rewrite 4/3 in terms of sixths, right? Because then I could actually deal with the numerators. So I can do that pretty easily, right? 4/3 is the same as 8/6. So let's just rewrite. So this equation now says 8/6 of x, or 8/6 times x, minus 5/6 of x. And let's just stay on this side of the equation, okay? So we're going to have an equals, right? Some other stuff, but let's just stay here. So 8/6 minus 5/6 is 3/6, right? We said we can because 8 minus 5 is 3, as long as we're dealing with the same thing, sixths. So 3/6 of x now equals something, right? And I can even go one step further, because I know 3/6 is the same as 1/2. So all this whole ugly thing is really another way of saying 1/2 of x, right? Or x over 2 is fine. So 1/2 of x equals, okay, what does it equal? Well, 2/5 minus 1/2. Well, 2 minus 1 is 1, 5 minus 2 is 3. So this all equals to 1/3, right? No, 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 no. You can't just add and subtract numerators and denominators. The only way that we can operate is if they have the same numerator. So 2/5, I have fifths and I have halves. Common denominator there is going to be 10. So 2/5, I want to write it in terms of tenths. So 2/5 is the same as 4/10. I can multiply top and bottom by 2, minus 1/2, which is the same as 5/10, right? Multiply top and bottom by 5. So 4/10 minus 5/10 is negative 1/10, negative 1/10. So I'm stuck with this equation, and I'm almost done, but I'm not quite done yet, right? How do I solve this equation? Right here. And, well, the same way that we used inverse operations, right, earlier, if I have 1/2 as a coefficient, I could, to get rid of it, I could divide by 1/2, right? Divide each side by 1/2, but then we're dividing by fractions, right? We have to flip and multiply and all this junk, right? Another way, sort of more elegant way of viewing this is, in order to get rid of 1/2, I can just multiply by 2. Now, of course, dividing by 1/2 is the same as multiplying by 2. So let's multiply each side by 2. What's nice here is the 2's cancel, right? 1/2 times 2 is just 1, and so I'm left with x equals negative 1/10 times 2 is negative 2/10, otherwise known as negative 1/5. So that is my final answer. Have a great week.